Hi, good morning, everyone. Sorry, good afternoon. Thank you for having Korea session today. This is Soo Jong. I'm the professor of Seoul National University. My group is working on climate modeling and global carbon cycle study. So today we have 4 speakers from different disciplines. The first speaker is Cherin Park. She is a PhD candidate of Seoul National University. And actually, she is the pioneer of the Seoul City, Seoul CO2 project. And she's now studying the urban carbon cycle by integrating the data and model. Actually, we started this project since 2019. At that time, Tom also visited our station, but it's a very beginning stage. So you can see the big changes today. Yeah, and second speaker is the Park Jae-pil, and he is the CEO of Nara Space Technology. And Nara Space Technology is the small company, but very promising company. I think Nara is the first CubeSat company in Korea, and they will launch the city level environmental monitoring system next year. Its name is Busan Satellite, right? Busan is the city name, and they will launch the Busan Satellite. That's the first city level CubeSat in Korea. And third speaker is the Seungmin Lee. She's a senior scientist of Korea Environment Institute. She's an expert on the subject of the transboundary transport of air pollutant related to the meteorological condition. And today, I think she will introduce the recent air quality and management policy in Korea. And final speaker is the Yu Young-soo. She is a senior research of National Institute of Environmental Research of the Ministry of Environment. And she is currently in charge of developing national level GHG monitoring network. In Korea, actually, we don't have satellite like as China and Japan. So actually, we don't have enough GHG observations. So our government decided to have ground monitoring system first. So actually, our territory is small compared to China and Japan and India. So maybe a reasonable ground system is help us to see the variation of greenhouse gas across the country. So today she will briefly introduce Korea's planning of national network. Okay, let's first have the speaker, Cherin Park. I think I can expect she is the youngest speaker in today. So please encourage her to have a nice talk. Thank you.
Hi, I'm Cherin Park of Climate Lab from Seoul National University, and I'm really honored to have a chance to talk this meeting today. And today I'm going to introduce our Seoul CO2 project on behalf of my team. So the reason why we are focusing on Seoul is because, as you know, cities are responsible for more than 70% of global fossil fuel-induced carbon emissions. And especially Seoul, which is the capital of Korea, is the world's 5th largest carbon-emitting city around the world. So monitoring of urban carbon cycle over Seoul should be proceeded to achieve effective carbon management of South Korea. Therefore, we established Seoul CO2 project to monitor and evaluate carbon cycle characteristics of Seoul. Our project is composed with 3 parts: carbon observation, inventory, and modeling system. So today I'm going to briefly introduce what we are doing on each part of our project. So first, I'm going to start with carbon observations, which we monitor and assessment CO2 concentration variability over Seoul. So our carbon observation system is divided into 3 parts by its observation scale. So the largest observation scale data is satellite, which is used to understand the comprehensive CO2 concentration characteristics of Seoul. And the second one is ground in situ observation, is used to know the real-time CO2 concentration variability of Seoul. And the last one is mobile observation, which is used to know CO2 concentration characteristic by road scale over Seoul. So first, the XCO2 data from over Seoul is validated by using EM27 Sun instrument. And EM27 Sun instrument is a ground-based instrument that measures XCO2 like satellite does. Currently, our project operating 2 EM27 Sun instruments at Seoul National University, and these 2 instruments are currently used to validate all the XCO2 data measured over Seoul from global satellites such as OCO and GOSAT. And along with satellite data, our project also produced ground CO2 concentration data by organizing ground observation network of Seoul. Our network is started since 2018 with 2 observation sites by Seoul National University. And currently, our network is expanded to 7 CO2 observation sites of Seoul by collaborating Korean government agencies. And they consist of 3 different instruments. One is SNUCOM, which is the low-cost CO2 sensor developed in this project, and others are instruments from LICO and Picaro. Our equipment is calibrated regularly using the same standard gases and method. And especially these 3 sites which uses SNUCOM instrument is located at high altitude, such as Namsan Seoul Tower, which is the tallest building in Seoul. So they are suitable for observing representative CO2 concentration of its region over Seoul. And this data from this site can be used to analyze not only the CO2 variability of its region, but also can be used to know the vertical CO2 variability of Seoul. And its sites are located to reflect various land use types in Seoul. And as you can see in this graph, its site measures different CO2 characteristics by its observation site. So the data from our ground network is currently used to evaluate the different CO2 characteristics over Seoul, and they are also used to evaluate of CO2 reduction effect by the implementation of its policy, such as social distancing policy during COVID-19. Lastly, we also established mobile carbon observation system to monitor high spatial temperature CO2 concentration over Seoul, where no in situ observations were made. Our mobile carbon observation system uses carbon-free electric vehicles with various instruments which measures CO2, CH4, NOx concentration, and wind direction and speed with 1 second time resolution. While moving through urban areas, our mobile system observes CO2 concentration with high spatial temperature resolution by load scale. Using our mobile system, we try to evaluate the spatial temperature variation of on-load CO2 concentration over Seoul. So we conduct intense mobile observation campaign over Seoul, and by using this mobile observation data, we calculate the on-load CO2 concentration of major load over Seoul. As you can see in this figure, the on-load CO2 concentration of Seoul is highly different by load and time, and they has different variation characteristics by its road type. So this result indicate that various information on on-load CO2 emissions, which is the second largest CO2 emission sector of Seoul, can be obtained through mobile observation that cannot be obtained by only use satellite or ground in situ observation data. So by using our carbon observation system, we monitoring and evaluate the variation of CO2 concentration over Seoul. And we also monitoring carbon emission and uptake flux over Seoul by producing inventory data. We make carbon emission inventory named ISAC, which is Inventory System for Counting Anthropogenic CO2. And ISAC produces 1 kilometer and 1 hour gridded carbon emission inventory for Seoul. ISAC estimates CO2 emission by multiplying activity data and CO2 emissions coefficient, and the estimated CO2 is distributed to 1 kilometer and 1 hour scale by applying proxy data. And as you can see here, ISAC will capture the major CO2 emission sources over Seoul, such as airport and power plant and congested road sections. And we also make carbon uptake inventory called CAS, which is Carbon Simulator from Space. And CAS produce 250 meter and 1 hour gridded carbon uptake inventory for Seoul. And CAS estimate carbon flux using satellite data-based carbon flux model, and they will capture the different CO2 flux variability over Seoul by region and time. So using our ground in situ observation and inventory data, our project also established modeling system that can evaluate the CO2 emission data like ISAC. So this is the schematic diagram of observed-based inverse modeling of our group. Our model uses ISAC and cost inventory data and our ground in situ data as a main input, and they produce optimized carbon emission with minimal difference in observed and simulated CO2 concentration. So this is the result from our inverse modeling system. The left side figure shows the prior emissions data of ISAC, and the middle figure shows the optimized posterior emission data from our model. And right side figure shows the amount of emission corrections, which means the difference from prior and posterior emissions. This result shows that our prior emission underestimate the CO2 emission of Seoul by 1.3% and 60.7% of uncertainty of prior emissions can be reduced by using our observed-based inverse modeling system. So to summarize, Seoul CO2 project which contains carbon observation, inventory, and modeling system, enabled to achieve an in-depth understanding of carbon cycle over Seoul. So ultimately, we plan to expand the Seoul CO2 project to country scale to monitor the carbon cycle over Korea. Thank you.
Okay, thank you, Cherin. Our next speaker is the Park Jae-pil, CEO of the Nara Space Technology. Yeah.
Thank you for having me. And because I am a very space tech guy, so it is very honored to present about the environment topic with the environment experts, you guys. So I'm Jeff Park, the CEO of Narrowspace Technology, and Narrowspace very focused on the CubeSat manufacturing under the 50 kilogram. Today I'm going to talk about why the CubeSat and CubeSat constellation system need for the environmental monitoring. Narrowspace founded in 2015, and recently we successfully second fundraised, and with 11 million US$. And Narrowspace participated in many CubeSat space-grade CubeSat projects as a mission designer and a system provider. And there are 14 university or commercial CubeSat mission what we participated. I want to introduce most recent mission, this video camera system mission successfully finished recently, and a few months ago, the second Korean satellite launch vehicle mission successfully finished, and the launcher was contained. The PV set was contained in the KSLV. It calls performance verification satellite PV set, and the PV set also contained 4 CubeSats, and Nara developed a video camera system for capturing the moment of a CubeSat development from the PV set. And this is the video clip of the moment CubeSat deployment. And there were 4 times deployment in space, and our system successfully captured all the moments. And same system also loaded Yonsei University CubeSat, and it works well until now. So finally, our video system and image data handling system fully verified in space environment. And we also manufacturing the deep space system like lunar surface magnetometer, and it will be loaded in NASA Eclipse mission's lunar lander for Artemis program. It also successfully finished ground tests, and it will be launched in 2024. And today my presentation is about the CubeSat system and constellation for environmental monitoring. I think the future environmental monitoring really need CubeSat and CubeSat constellation data. To reach the net zero, the most important thing is to surveillance emission source each other countries. But the current monitoring system is focused on a global trend of GHG monitoring by using observatory and big satellite. And it has some limits and not enough for emission source monitoring. With the point of view of satellite system, current satellite have big size and high spectral resolution satellite like Landsat or Moody's. It is good enough for global monitoring, but they are not suitable specific emission source because not enough spatial resolution and temporal resolution. So this is the point what CubeSat constellation can supporting current GHG monitoring system. So global satellite environment monitoring readers like USA or Europe preparing various level of satellite monitoring system, and recent new satellite environmental monitoring projects like methane set, GH set, or carbon mappers are all to target the area mapping or point source mapping. And this is the one of the sample CubeSat sample of CubeSat constellation, and this is not just animation clip, and this is a simulation by using Free Flyer, which the real satellite vision analysis program, and it considered field of view of camera and the attitude of CubeSat's orbit. If we operate 12 CubeSats with 3 orbital plane like this, and we can reduce the revisit time to under the 1 hour. And video shows that we can obtain the image of 3 cities in 3 Asian cities every 30 minutes in average. And if we operate more satellite, we can if we operate more satellites, and we can observe more cities, or we can reduce the revisit time. And so the most important thing for the CubeSat constellations are the stable system and mass production capability. So Narrowspace will verify our system through the 2 environmental Cube satellite missions. One of the mission is Busansat project, and the mission objective is to obtain the fine dust monitoring and for the Busan port, and the super thin cloud for climate modeling. Busansat contained very special payload, and it calls PORCAM, and it is very sensitive with aerosol because it can detect the polarized ray, and PORCAM is modified version of a lunar creator camera by Korea Astronomy and Space Science Institute. And this is the final configuration of Busansat, and we finished the whole development process, and it will be shipped to NASA Langley in next January, and it will be launched in the Q2 of 2024. And the other mission is Observer 1 mission, and it has microwave size and high spatial resolution for CubeSat level, and it has 7 multi spectral bands, RGB and NIR, and 3 radiation bands for NDVI monitoring. And the observation 1 is our standard constellation satellite. So it will be launched in next October 2023, and with SpaceX Falcon 9 at the California Vandenberg launch pad. And this is the video clip of Observer 1 assembly. And if the system will be verified through 2 missions, and we can manufacturing 1 verified satellite system in a day with 5%, like a Lego assembly. And we mainly use commercial grade parts of commercial grade parts. Of course, we do not directly use the parts. We conduct space radiation tests like this, and this video is process of total ionized test, and we expose the chipset in gamma ray environment until which they made a malfunction like this. This is the normal image and malfunction the image. And we can check after that we can check the limit of the chips catalog. And the ground support equipment is also very important for the mass production. And this is the example of our electrical ground support equipment and its interfaces. And it can test 10 to 20 electrical board at once, test at once, and we can check the board condition and errors very fast. Then we have many facilities in Busan headquarters for the 10 CubeSats. It can integrate 10 CubeSats at once in this factory. And hyperspectral camera also is very important part of environmental monitoring, and CASI is one of our good payload partner. So CASI already experienced the space NIR camera like MIRIS and NIS. So this is my final slide, and we want to operate 100 satellite at least in 5 years. And constellation will be mixed optical and hyperspectral payload for GHG monitoring. And NARA Space is ready to environmental constellation mission, and we are very open any collaboration. Thank you for your attention. Thank you.
Okay, thank you, Jeffrey. Next speaker is Seungmin Lee from Korean Environmental Institute. She will have a talk about the air quality management planning in Korea.
Good afternoon, everyone. Thanks for the opportunity to introduce the policy of air quality control in Korea. Okay, my presentation is divided into 3 parts: the past, present, and the future of Korean air quality and management policies. Firstly, I'm going to talk about changes in air quality in Korea over the past 20 years, from 2000 to 2019. The history of air pollution control in Korea goes back well over 20 years. As you all know, the World Cup matches are being held in Qatar right now. By the way, the World Cup match was also held in Korea in 2002. I think that this was the first trigger for national air pollution control. The Korean government had to make the air clean so all soccer players could play well. I think that the second policy turning point, is the implementation of the fine dust forecasting system in 2014. Since many people have been interested in PM air quality and worried about air pollution. As you can see from this diagram, the government has announced new fine dust policies every year from 2016 to 2019. In particular, in 2018, 8 laws related to fine dust were newly enacted and revised. In addition, a government organization for fine dust management was newly established. As a result, the PM10 and PM2.5 concentration has steadily decreased over the past 20 years. However, it stagnated somewhat between 2018 and 2019 with no change in concentration. The concentration of PM2.5 does not meet the national standard, so further improvement was required. As you can see from this chart, the number of good days nearly doubled from 2015 to 2019, and the number of bad days fell by 30%. However, the number of very bad days with 75 microgram per cubic meter or higher continued to appear. Therefore, the need to respond to high concentration fine dust has been raised. This leads me to the following part. Is there any problem? The second part is the current air management policy and air quality status in Korea from 2020 to 2021. For a long-term and systematic battle to fine dust, the government established a fine dust management master plan from 2020 to 2024. About 100 reduction measures for each sector were developed to achieve the concentration target for 2024. Our goal for 2024 is the 35% reduction of annual average concentration of PM2.5 compared to 2016. According to the master plan, various new policies were promoted by field and sectors. Due to time constraints, I will omit these slides. As you can see from this graph, the nationwide annual average concentration of PM2.5 decreased from 23 microgram per cubic meter in 2019 to 18 microgram per cubic meter in 2021, recording all-time low value. 2021, the number of good days for PM2.5 was 183 days, recording a 59% increase compared to 2019, and a 190% increase compared to 2015. In particular, the very bad days with the PM2.5 concentration of 76 microgram per cubic meter or higher occurred on only one day between 2020 and 2021. We can estimate the cause of the recent air quality improvement as follows. First cause is the impact of the implementation of policies according to master plan. This graph illustrate the changes in emission of air pollutants such as PM, SOx, and NOx. A clear decrease can be observed. The second cause is the impact of air quality improvement in neighboring countries. It is estimated the amount of air pollutants originating from outside the country has decreased due to the active improvement efforts by neighboring countries, such as China. The third cause is the impact of good weather condition. In the summer and early fall of 2021, from August to October, the east wind increased, allowing the frequent inflow of clean air and contributing towards lowering the concentration. What about the impact of COVID-19? The operation rate of the manufacturing industry in Korea and nationwide highway traffic recorded low values in the first half of 2020 and gradually increased thereafter. Therefore, the impact of COVID-19 is estimated to have two significance in 2021. So far, I've talked about past and present. What about the future? Lastly, I'm going to more on to the future changes in air quality management policy. In order to discuss future policy directions, we must look into changes in the major internal and external conditions. First major change is the spread of an infectious disease. A diverse range of face-to-face activities stagnated due to concerns over the spread of infectious diseases. The territorial and recovery repeated according to the epidemic of variants. The global economic recession and supply chain crisis caused by the continued pandemic. Due to the increased indoor activities, health risk and indoor air quality management issues garnered attention. The second change is the plan for carbon neutrality. As the major countries around the world joined focus to achieve carbon neutrality by 2050 in October 2020, Korea also declared to achieve carbon neutrality by 2050. Power generation, industry, buildings, and transportation sectors that seek innovation for transition into a low carbon structure are sources of greenhouse gas emissions as well as air pollutants at the same time. Therefore, it is necessary to ensure the consistency of carbon neutrality and air quality control policies in a considerable number of projects. The last change we need to consider is the new government's national projects. On May 2022, the list of 120 national projects was announced after the inauguration of the new government. According to the national project number 88, the government must reduce PM 2.5 concentrations to 13 micrograms by 2027. So we need to develop stronger air pollution reduction policies. Considering these internal and external changes, we will continue to improve our air quality management policy. Okay, that ends my talk. Thank you.
Okay, next is the final speaker, Yu Young-soo. She will have a talk about the carbon neutral policy and science-based network, right?
Good afternoon, everyone. I'm Young-suk Liu from National Institute of Environmental Research, Ministry of Korea. Thank you for inviting me to this meaningful GEMM Asia Summit. I will briefly introduce Korea's carbon neutral policy regarding ground-based greenhouse gas monitoring. We are running out of time, so I will finish my talk very quickly. Korea's total greenhouse gas emission in 2019 was 713 megaton CO2 equivalent, and energy and industrial process were key sectors for greenhouse gas emissions. As you know, 2030 nationally determined contribution and intermediate goals for the realization of carbon neutral by 2050 based on the Paris Agreement. Korea implemented Framework Act on Carbon Neutrality and Green Growth last year to legislate carbon neutrality target, which is reducing greenhouse gas emission by over 35% from the 2018 levels by 2030. And Korea decided its NDC to reduce greenhouse gas emission by 40% by 2030 compared to the levels in 2018, which is very challenging goal when compared to other major countries, given that the annual average reduction rate of the NDC enhancement plans is 4.17% per year. In order to achieve NDC, Korea plans to implement mix of domestic and overseas reduction measures together. As I mentioned before, Framework Act on Carbon Neutrality and Green Growth, the legal basis of tackling climate crisis and achieving 2050 carbon neutrality, was proclaimed in September 2021. The Act specifies procedures of implementing 2050 carbon neutrality vision, detailing the establishment of the Carbon Neutrality Commission and the framework plan. Various policy options for climate impact assessment, climate response fund, and just transition are also included in the Act. And the Act proposed climate crisis adaptation policies measures, including atmospheric measurement of greenhouse gases. Article 37 mentions monitoring concentration of greenhouse gases in the atmosphere. Accordingly, we are building a nationwide ground-based monitoring network to observe greenhouse gas, and we are conducting assessment result to design optimize the nationwide monitoring network. And monitoring indexes are developed to select optimal numbers and placement of greenhouse gas monitoring sites. Carbon emissions and the size of the area of the region are considered as the main factors. Monitoring Index A is developed to select the optimal number of greenhouse gas monitoring sites, depending on the amount and the regional variation of carbon emission at each province. The table shows optimal minimum and maximum numbers selected for each region. Monitoring Index B is developed to select optimal placement of greenhouse gas monitoring sites, depending on the surface area of the regions. The optimal number of sites, not only depending on the surface area of the region, For example, these two regions has the same optimal number of sites, but the surface area is quite different. And the optimal numbers of sites also not only depending on the amount of carbon emissions. For example, these two areas has similar greenhouse gas emissions, but a different optimal number of sites. We have established Greenhouse Gas Research Association to conduct pilot observation in Seoul area. Previous speaker, Dr. Cherimbak, mentioned before. At first, we had only 4 members, National Institute of Environmental Research and Seoul National University and Seoul Metropolitan Government and National Forest Research Institute. Now we have 11 members, other regional province, government and other research institutes joined recently. The future plans are as follows. First, evaluation of greenhouse gas monitoring sites. To evaluate, optimize new monitoring sites and conventional sites that already were established to research air pollution. Second, expansion of urban greenhouse gas monitoring nationwide. 12 ground-based monitoring sites will be operated by National Institute of Environmental Research by 2024. And we will also expand the Greenhouse Gas Research Association. We'll expect more regional government will join the association. And lastly, we will establish a national standard method to measure greenhouse gas at urban area. That's my talk. Thank you for your attention.
Please come here. Thank you for listening for your session. Actually, we spent too much time. Everybody should be boring and tired. We have to take a rest. Okay, please give a short session.
Yes, thank you. Thanks for the very comprehensive overview of Korea efforts to mitigate climate change and improve air quality. Regarding to carbon dioxide validation systems, I'm curious, why about a network of monitor sensors? Yes, we need to monitor, we need to measure atmospheric concentrations, but it's not just playing a bunch of sensors. I understand that they should be deployed according to the inverse modeling needs. So that's my first point. It's not, I guess we should look for a smart way of finding where to locate those stations. And I understand that inverse model requires measurements at a certain height to be very representative. And also, I know that Korea is taking the lead in eddy covariant flux towers. Seoul, I think, is the city with most active flux towers in the world so far. I didn't see any of the flux towers data on the carbon on the Seoul CO2 monitoring system. Thank you.
Actually, we have I think 10.
Yeah,
10 flux towers in Seoul. We also use that data to validate our model. So, but you know, you can expect it will take labor and cost problem. So we cannot increase the number of flux tower. So we use the concentration sensors and with modeling.
Because maybe 10 flux towers are more than enough, and they can provide you useful data to validate
Right,
the
right.
accuracy of your bottom-up
Yeah.
emissions inventories.
Okay, yeah, I see. Thank you. Any question? Yeah.
Yeah, thank you very much for the very interesting talks. And I'm curious about your new designing of the CO2 monitoring network, how to put the new stations over the countries or cities. And so, yeah, if of course, the resource, so you have enough resources, you are able to design as much as you can from that ideal setup is possible. But another idea would be to use the currently existing the monitoring network of the air pollution. And yeah, sometimes we believe that even the CO2 has a common sources with the pollutants and can behave similarly, but not always, I would say.
Yeah.
But yeah, that can be one possibility to analyze particularly for which sectors the CO2 is coming, and yeah, other locations, maybe the other sectors could be important. So yeah, I'm asking if you have considered such another possibility to use the existing pollution measurement sites to add the CO2 monitors there, or you decided not to use that. Because in Japan there is no such a CO2 monitoring network yet. So I'd like to learn from you
You have to
of
settle
your
it.
way of thinking.
Thank you for your question. As you know, in Korea, we have already more than 500 air pollution monitoring sites nationwide. And as you mentioned, we also can use that site as the greenhouse gas monitoring site, and we can use greenhouse gas emission, greenhouse gas monitoring data, and also air pollution monitoring data simultaneously. So of course, we are considering using the site, present site, yes, air pollution sites, yes. Thank you.
Azizam, thank you very much for assembling wonderful the panel discussion too, and also the speakers, they're wonderful. This is a great example of say the science and also the policy side, how to collaborate. My question is pretty simple, especially I want to ask the last two speakers talking about more policy. And the first two speakers talk about more like technology, science. They developed the tools to informing greenhouse gas information that you can even measure things from satellite. And what would your reaction to those things? Then if you guys have already have conversation, then how that goes so far? And especially goes, I believe the two speakers presented really important, useful tools for you guys to do the policy making. So I just wanted to hear your reaction. Last two speakers. You can talk to. Yeah, Sujun can help if you want.
Thank you for your question. Actually, air pollution monitoring is very important to reduce air pollution. Air pollution is very hazardous for the human health, so we need to monitor very we need dense monitor for the reasons, but until now we monitor the greenhouse gas only for the global level for the climate change. But now we need to assess the carbon neutrality policy for each regions or regional level or national level. So we need more observation data for that purpose. So as you know, the IPCC already recommend the verification of bottom-up inventories with top-down observation-based inventories. So we need greenhouse gas observation data. So this is very important to get more data, I think. Yes, so we can use those data for the policy assessment. Yes.
Okay, we can stop here. No more question? Okay, thank you for listening us. We want to stop here. Yeah, thank you.
Right, thank you for the speakers and the moderator for the past two sessions. So now we have a short break. Let's caffeinate it for the last part of the today's session. So we're gonna come back in with 10 minutes. Yeah, so it's let's say 10 minutes. So now it's a little funny time. So yeah, 3:50 Singapore time. We come back to the room. Thank you.